Hello, my name is Alex Dorsey, and this is Physics 2211 Lab 2, Motion of a Falling Object. The purpose of this lab was to analyze the motion of a falling object and determine the effects of drag on that object. In this lab, we compared an observational model of a falling motion with two other models, one model which is computational without drag, and another computational model with drag. In this lab, we assumed that there was no side-to-side motion or motion in the x direction, and that there was only motion in the y direction. Some of the key concepts for this lab is Newton's second law. The momentum principle states that the total force is equal to the change in momentum over the change in time, and this is related to the velocity update formula, which relates velocity to force. And then the position update formula is also related to the velocity update formula as well. Another key concept for this lab is gravitation. The force of gravity is given by negative mg times the direction of the unit vector. And then we can also find the force of gravity using the universal law of gravitation, gmm over r squared. And then using that, we can find the acceleration due to gravity on Earth. And then finally, the drag force is caused from particles in the air acting against an object, and the direction of drag force is always opposite to the direction of the motion, and in this case that's going to be an upward force that opposes gravity. In this lab we'll model the drag force through that equation, and in the free body diagram you can see that as time moves forward the drag force increases. So for this lab I basically crumpled up a piece of paper and just dropped it, and I used tracker to track the motion. The ball's mass was 0.025 kilograms, its diameter was 0.04 meters, its initial position was negative 2.493 times 10 to the negative 5 meters, and its final position was negative 0.535 meters. Its initial velocity was 0 meters per second, and each frame was around 0.033 seconds, and then the time of the last observation was 0.367 seconds. In this lab, the system is the crumpled piece of paper, and the surroundings are the air, the earth, and just everything else in general. For the computational model with no drag, the initial conditions were basically copied from tracker, and noticeably the b value is 0 because we are not accounting for drag in this model. And then the iteration steps include Newton's second law with the velocity update formula and the position update formula. With the model with drag, we have basically the same initial conditions. However, we also have a non-zero b value, which will add to the drag force. And then again, we have the Newton's second law equations to update the velocity and the position. And also we have a new F net, which is taken by adding the force of gravity and the force of drag together. So when we compared all of the models together, we see that the observational model is in yellow, the model without drag is in red, and the model with drag is in blue. We can see that the model without drag has a greater magnitude of velocity, and the model with drag has the least magnitude of velocity. So in conclusion, we can say that the computational model without drag has too steep of a slope to account for what we observed, but also the observed model is more similar to the drag model, but it begins with a higher initial velocity. And some of these errors could be accounted for an inaccurate drag coefficient value, any video distortions, and then tracker error such as not clicking the exact center each time of the crumpled piece of paper. So now for the discussion questions. First, which model predicts terminal velocity? The drag model predicts terminal velocity, and we can see that by looking at the graph that it produced, the velocity versus time graph that it produced, because we see that it begins to approach a constant value, whereas the no drag model, the velocity just continues in a straight linear path. And then for the second discussion question, does initial velocity affect terminal velocity? No, the terminal velocity is not changed based off of any initial velocity because terminal velocity is based on when the net force between gravity and drag cancel out and are in equilibrium, and that has nothing to do with how hard you throw it initially. If you were to throw it down, then that object would simply just reach terminal velocity quicker than that same object being released from rest. And you can verify this by changing the code, the model, the initial velocity to 0, -1, 0, and you can graph that and see that the results are the same.